to welcome today's speaker, Nathan Ilten, who's going to talk to us about cotangent cohomology for Stanley-Reisner rings. So thank you, Nathan.
Yeah, thank you very much for the invitation, and thanks to everyone in the audience for coming to listen. So what I'm talking about is very much work in progress. It's joint work with Francesco Meazzini from Rome and Andrea Petracci from Bologna, both of whom I think have joined online. So if you have difficult questions, you should ask them. And yeah, so I'll be talking about cotangent cohomology for Stanley-Reisner rings. I don't expect that you know what any of these words mean just yet. So the first part of the talk, I'm going to spend explaining a little bit about cotangent cohomology. Then I'll tell you what a Stanley-Reisner ring is. And then I'll try and tell you something about how to actually compute cotangent cohomology for Stanley-Reisner rings. And yeah, if at any point you have questions, please do feel free to interrupt me, put the questions in the chat, or just shout them out, and I'll try my best to answer them. Okay, so let's dive right in and talk about cotangent cohomology. So my setting is going to be the following. We're always going to be working over some field K. So this is a field, and we're going to assume that it has characteristic 0. And I know that in your seminar, many of you are working sort of in the non-commutative setting. I come from algebraic geometry. So for me, rings and algebras typically are commutative. So S is going to be a commutative K algebra. And yeah, most of the time we'll probably be assuming that it's also finitely generated. That makes a couple things simpler. And so, yeah, what is cotangent cohomology? So first of all, just some notation. So Ti of S, so here I is some non-negative integer. Ti of S is the ith cotangent cohomology module of S over K. And so just to give you some first things about this, so this is a finitely generated S module for each I. And the 0th version, so T0 of S, this is just K derivations from S to itself. For higher indices I, Ti of S is some kind of like some kind of derived functor of this derivation functor. I'll make that precise in a minute. And just to write down some names here, so for I less than or equal to 2, these were first defined by Lichtenbaum and Schlesinger. And then in general, these were done independently by Andrea and Quillen. And actually frequently this Ti of S here, this is called also Andrea Quillen cohomology of the algebra S. Okay, so this is an interesting cohomological invariant of the algebra S. I'll talk a little bit about some motivation for why these are interesting in a minute, but let me at least attempt to give a definition of what these are. Okay, so in order to define this, we need a little bit of something from homological algebra called a Koszul-Tate resolution. So we need what's called a Koszul-Tate resolution of our K algebra S. And so this will be something that I'll denote like this, P dot going to S. And I'm going to take at least a couple minutes telling you what this is. Okay, so what is this P dot? So this is a graded commutative algebra. So everything is over our field K. And so what does that mean? That means it's going to be some direct sum. Here I'm going to use homological convention. So my indices are going to be non-negative. Right, and so it's an algebra It's graded. That means that it decomposes as a direct sum like this. This direct sum respects the multiplication, and being graded commutative means that things commute up to sign. So things of even degree commute, things of odd degree anti-commute. Okay, so that's what this P dot is. And to be a Koszul-Tate resolution, I want a little bit more. I want it to be free. Okay, so that means that the only relations that you have are the relations that are induced by this commutativity rules. And I also want it to be equipped with a differential. So this is equipped with a differential d from P dot to P dot. So this is, again, using homological convention. So di goes from pi to pi minus 1. And so this should be a differential in the sense that if I compose d with itself, it becomes 0. It should also respect the algebra structure in the sense that the differential satisfies the graded Leibniz rule. So I'm not going to bother writing this down, but this is an important restriction on the differential. Okay, and so this is what the P dot is. So a Koszul-Tate resolution of S is one of these three graded commutative algebras equipped with a differential together with a map of differential algebras from P dot to S. So I can view S as a differential graded algebra with everything just concentrated in degree 0. And I want this map to be a quasi-isomorphism. So in other words, if I look at H0 of P dot, this should be isomorphic to S, and Hi of P dot should be equal to 0 if I is not 0. Okay, so this is what a Koszul-Tate resolution is. And the idea is if I want to do some kind of like derived functor thing, instead of using this object S, I should replace it by this model P dot, which somehow has much nicer properties. Okay, so now how do we get cotangent cohomology? So we can take our Koszul-Tate resolution, which I'll just denote now by P. I'm going to drop the dot. And we can look at k linear derivations from P to S. Okay, so again, this is a graded commutative algebra. And so these derivations, again, need to satisfy sort of a graded version of the Leibniz rule that I'm not going to write down. Right, and within this space of all derivations, I can look at those derivations that take, say, the degree I piece of P to the degree 0 piece of S, and I'll denote that by der I. Okay, and so if I take the direct sum over all of these, let's call this der dot. Okay, and so this, the differential on my algebra P induces a differential on this derivation complex. And so now we can define the ith cotangent cohomology of S just to be the ith cohomology of this derivation complex. Okay, and so it's, first of all, this is not quite the same way that this was originally done by Andrea and Quillen. They used simplicial algebras to define cotangent cohomology, but this turns out to give something equivalent. And it's a theorem that this doesn't depend on the choice of Koszul-Tate resolution up to canonical isomorphism. Okay, so this is what what cotangent cohomology is. So I'll give some motivation for this in a minute, but I wanted to make two remarks. So the first remark is due to a theorem of Abramoff, which is that these Koszul-Tate resolutions that we're thinking about are in general quite complicated. So if you're thinking about sort of typical derived functors, if you have a module over a polynomial ring, Hilbert's syzygy theorem tells you that you can actually find a finite free resolution of this. And so when you're thinking about derived functors in that setting, somehow there's only finitely much homological information that you need to encapsulate. But Avramov's theorem says that actually, if you want to make a Koszul-Tate resolution, you're going to need generators in arbitrarily high degrees, unless you're in the situation of a local complete intersection algebra. So let me write that down. Avramov says that you need generators of this Koszul-Tate resolution in arbitrarily high degrees, unless S is locally a complete intersection algebra. So that means a quotient of something smooth by a regular sequence. Sorry, was there a question? No. Okay. So in any case, these Koszul-Tate resolutions are something complicated, and so that means by association, this cotangent cohomology is also something rather complicated. The second remark I wanted to make connects this to Hochschild cohomology, because I know there's a bunch of people in the audience who think about this. So in the commutative setting, Hochschild cohomology actually has a direct sum decomposition called the Hodge decomposition. And this cotangent cohomology shows up as a direct summand in this decomposition. So Ti of S is a direct summand of HHI plus 1 of S. So there's a shift of indices, but this is, this is a connection to Hochschild cohomology. And we'll see sort of an interpretation of this in a second, at least when I is equal to 1. Okay, so let me now talk about a little bit of motivation for cotangent cohomology. And so for me, the motivation comes from deformation theory. And so let's go ahead and define what I mean by a deformation. So let's say A be a local Artinian K algebra with residue field. So if M is the maximal ideal, I want the residue field just to be isomorphic to my ground field K. And so we'll say a deformation of my algebra S over this Artin ring A is a flat A algebra S twiddle together with an isomorphism from S twiddle tensor over A with the residue field back to my original algebra S. So the idea is I've started with my algebra S. I'm thinking about this as a K algebra. Now I want to replace K by this sort of slightly larger algebra, A, this Artinian K algebra, and thicken out my algebra S to an algebra S tilde living over A, so that when I restrict back to the residue field, I get back S. Okay, and so this is what a deformation is. And so the connection to deformation theory is now the following. So it turns out that, I should say, there's a natural notion of isomorphisms of deformations. I'm not going to write it down, but I'm sure that if you tried to think what it would be, you'd write down the correct thing yourself. So T1 of S turns out to be equal to the set of all deformations of S over the simplest non-trivial Artin ring, which is kt mod t squared modulo isomorphism. Okay, and a comment here is in order. So here, like I said, everything in my talk is going to be commutative, or at least graded commutative. And so this A algebra that I'm thinking about, S tilde, I want that to be a commutative A algebra. And so here we're looking at commutative deformations of this A algebra, of this K algebra S. If you included non-commutative deformations, then you'd be getting exactly the second Hochschild cohomology. So H2 of S gives non-commutative deformations of S, again, over this ring of dual numbers, kt mod t squared. Okay, and so having T1 of S sitting inside H2 of S reflects this fact. Okay, so this is for the first cotangent cohomology module. What about for the second cotangent cohomology module? So let's consider a deformation, say S tilde of S over A. So now, given any extension, so I'll start with my Artin ring A, and I'll look at some extension of it to a larger Artin ring, whose dimension over K is exactly one more. So my kernel here is just K. Let's call this eta. There exists some element, I'll denote this by O of eta, that lives in T2 of S. And this is this O of eta, this is assigned in sort of a systematic functorial way, such that O of eta is equal to 0 in T2S if and only if my deformation S tilde can be lifted to a deformation over A prime. So this second cotangent cohomology module contains the information about obstructions to lifting deformations. So in particular, if T2 of S is equal to 0, then every possible deformation lifts. Okay. So this was T1 and T2. In the latter part of this talk, I'm actually going to be talking mainly about higher cotangent cohomology. So Ti when I is larger than or equal to 3. So then there's not quite as much of a direct connection to deformation theory, but the higher cotangent cohomologies actually still do give some useful information in deformation theory. And I wanted to give one example of this. So here's a theorem that's due to Kurt Benke and Jan Christophersen. It says the following. So let S be a K algebra with an isolated singularity. Maybe I want it to be local. Let's say a local K algebra with an isolated singularity. And so this means that this ring is regular at all prime ideals except for the maximal ideal. And let's say F be some element of S that's not a zero divisor. Zero divisor. Such that if I look at the K algebra S prime that I get by taking the quotient of S by F. This also just has an isolated singularity. Then if for some I, Ti of S is equal to Ti plus 1 of S is equal to 0, it follows that Ti of S prime is also equal to 0. So the upshot of this is, if I want to know something about cotangent cohomology of this quotient algebra, I can obtain it by knowing something about the cotangent cohomology in the same degree and in 1 degree higher for the original algebra S. So in particular, if I wanted to know that, say, S prime had T2 equals 0, so all deformations lift, I could check this by seeing that S itself has T2 equals 0, but also T3 equals 0. And so this is one place where these higher cotangent cohomology modules are quite useful. And so you can sort of apply this inductively to think about complete intersection rings as well. Okay, so this is everything that I wanted to say directly about cotangent cohomology and some motivation for it. And I'm going to switch gears now to Stanley-Reisner rings, but let me also just pause for a second to see if anyone has questions.
Hi, Andrea. This is Hipólito. Sorry, I got late. Yeah, I have a question for you there. Is there a consequence of a non-exact sequence of some sort of?
Yes, exactly. So cotangent cohomology has all kinds of nice functorial properties. And really, let me write some other notation here. So this, what I called here, this Ti of S, this would be Ti of S with values in S. And you can also think about cotangent cohomology with values in a different in other S modules as well. So there's TIS of M. You'd get this by where is it? Here replacing this S with an M. And so this gives you a bunch of long exact sequences. There's also one. So here I was taking cotangent cohomology relative to the ground field K. Anytime you have just a map from one ring S to another ring S prime to a third ring S double prime, this also gives you a long exact sequence. And so combining things like this basically gives the result. Yes.
Right. Thanks.
Yeah. Okay, so let's switch gears and start talking about Stanley-Reisner rings. So if I lost you in the first part, you can start listening again, because this is now going to be something completely different. Okay, and so let me start by reminding you what a simplicial complex is. So definition. A simplicial complex, say X, on the vertex set from 1 up to n, is a collection of subsets of X, a collection of subsets of 1 up to n that is closed under taking subsets. So let me give an example. And the way that I'm going to give this example, that we're going to think about any simplicial complex, is always actually in terms of a picture. So let's say that maybe n is 4. And so here's 1, 2, 3, and 4. And I'm going to draw in this picture all the things that belong to X. Okay, so what sets belong to X? So each of the singleton sets, 1, 2, 3, and 4, belong to X. So do the sets with 2 elements, 1, 2, 2, 3, 1, 3, and 3, 4. But for instance, the set 1, 4, this does not belong to my simplicial complex. And finally, the set with 3 elements, 1, 2, 3, also belongs to X. Okay? And so this is a collection of subsets of 1, 2, 3, 4 that's closed under this property of taking subsets, right? Since 1, 2, 3 belongs to my simplicial complex, then any subset of that does as well. All right, so this is a nice combinatorial thing. And so even though I can think about these things quite abstractly, as you see, for each one of these, I can draw a very nice picture and think about the simplicial complex also as a topological space. And this will be important later. OK, we want to somehow translate this into algebra, though. And so given a simplicial complex X, we can form what's called the Stanley-Reisner ideal. So I'll denote this by Ix. So this is going to be an ideal in the polynomial ring over K with one variable corresponding to each element in my vertex set. And so what are generators for this ideal? This is going to be generated by certain products of the variables. So here I'm taking I and F, xi, and what's F? So F is some subset of my set 1 up to n. And I want F to not be in my simplicial complex. Oh, yeah, so sorry, I should have said this earlier. So we'll call elements of the simplicial complex X are called faces. OK, so what am I doing here to generate this ideal? I'm taking the non-faces and taking the product over all the variables that belong that belong to this non-face. Let's look at an example. OK, so starting with the first example that I have here, what do I get? So I'll notice that, say, 1, 4 is a non-face. So I get x1, x4. Likewise, I get x2, x4. And this is it. I mean, so the set, say, 1, 3, 4. This is also a non-face. And so in my ideal, I would also get x1, x3, x4. But we see that we actually don't need this one because this is already generated by x1, 4. Okay, so if I want to take a minimal generating set, I need to look at the minimal non-faces of my complex and take the corresponding monomials. Let's do one more example. So the second example is going to be a recurring example throughout the talk. So I'm going to take my simplicial complex to be the boundary of a hexagon. So I have maybe 1, 2, 3, 4, 5, 6. Here are the vertices. And so what are the minimal non-faces here? The minimal non-faces are things of the form I to I plus 2. So here I can take my indices modulo 6 and I to I plus 3. Right, so for instance, this is a non-face. So that gave me x1, x3. This is also a non-face. That gives me x1, x4. And so these are the generators for this ideal. OK, so now that I have an ideal, I can form the so-called Stanley-Reisner ring. Let me switch back to black. And I get this just, so I'll call this Sx. And I get this by taking my polynomial ring and taking the quotient by the ideal Ix. OK, so this is some interesting algebraic object that we've obtained from this combinatorial data. And many of the interesting algebraic properties that Sx has, you can read off of the combinatorial data. So for instance, the dimension of this ring is equal to 1 plus the dimension of the simplicial complex. So the dimension of any face, let me put this up here. If I have some face in my simplicial complex, the dimension of the face is just equal to the number of elements in the face minus 1. Right? This sort of checks out with this picture here, where this face with 3 elements looked like it has dimension 2. And the dimension of the complex is just the maximal dimension of any face. Okay, so that's one example of an algebraic invariant that we can read off from the combinatorics. And so,
sorry, by dimension you mean like full dimension of the ring?
That's right, Krull dimension of the ring. That's right. Yeah. And so you can ask many other interesting things. You can ask, like, what's the Hilbert function of this ring? You can ask, is this ring Cohen-Macaulay? And these are all things that have rather straightforward answers in terms of the combinatorics. You could ask something more complicated. For instance, what does the cotangent cohomology of a Stanley-Reisner ring look like? And that's what we're going to spend the rest of today talking about. Okay, so let me make that a little bit more precise, in fact. So notice that our polynomial ring kx1 up to xn comes with a z to the n grading, where the degree of a variable xi is just equal to the ith standard basis vector. So this is something that's much finer than the usual z grading that you think about in a polynomial ring. And now the point is that the generators for our ideal ix are homogeneous with respect to this grading, since they're all monomials. And so that means that this Zn grading descends to a grading on the Stanley-Reisner ring. So this gives a grading, a Z to the n grading, on Sx. Okay, and this means that also any kind of module that's defined canonically from this ring also will inherit a Zn grading. In particular, our cotangent cohomology modules, Ti of S, are also Zn graded. Okay, so here's some notation for some weight vector C in Z to the n. We'll let Ti C of x denote the weight C graded piece of Ti Sx. Okay, so the idea is now, right, if I'm interested in Ti Sx, we can split this up as a direct sum over all weights p in Z to the n of these Ti C x's. Okay, so we've split it up into this direct sum of graded pieces. And our goal is going to be, at least in favorable situations, to give a combinatorial interpretation of what these graded pieces are. So goal, give some combinatorial description of TICX. Yeah, so one nice reason that you might want to split things up like this is, okay, so this TISX is a finitely generated S module, but each one of these graded pieces, it turns out, is actually going to be a finite dimensional K vector space. And so this makes it something that we can perhaps deal with in a much nicer fashion. All right, so what I'd like to tell you about next is some existing results on cotangent cohomology so for T1 and T2 for Stanley-Reisner rings due to Klaus Altmann and Jan Christophersen. And to do this, I need a little bit more notation. So there's two things I need. So first of all, if F is some subset of 1 up to n, then there's a subcomplex of my complex X called the link of F in X. So what is this? This consists of all faces G in X, such that the intersection of F and G is empty, but the union of f and g belongs to the complex X. So let's look at our example. Right, we have our hexagon here. Let's take the link of this vertex here up at the top. Okay, so what's the link going to be? The link is going to be just the union of these two vertices here, right? Each one of these vertices, it's certainly disjoint from the red vertex. If I take the union of either of these blue vertices with the red vertex, I get one of the edges of my complex. But of course, there is not an edge between these two vertices because that doesn't belong to my complex. Okay, so that's the link. The link gives some kind of local information about the complex around subset. I'll also point out that if my F was something that didn't belong to the complex in the first place, then the link is just empty. There's nothing that happens. Okay, so that's the link. The other piece of notation I wanted was the following. Right, so if I start with one of these weight vectors, c and z to the n, then in fact there exist unique a and b in z to the n with non-negative entries, such that c is equal to a minus b. So any one of my weights I can split up into a positive part and a negative part, and that's what I'm doing here. And so anytime you see a c and an a and a b in the top, that's what this means. A and b will always have non-negative entries, and I've written my c as something non-negative minus something else non-negative. Okay. So I'd like to now summarize the results of Altmann and Christophersen on cotangent cohomology for Stanley-Reisner rings. And so these results are from roughly about 20 years ago. And yeah, this is really just a summary, and I'm sort of phrasing things in a way that fits nicely with the theme of my talk. But I think I'm really covering the most important points of their work. So I'm going to give 3 statements. And the first statement says the following. So yeah, so let's say X be a simplicial complex, and C equals A minus B be one of these weight vectors. So the first statement says for I equals 1 or 2, TIC of X is equal to 0 unless B only, so the negative part, only has entries in 0 and 1. Okay, so this really puts a restriction. So if you're interested in situations where you have non-zero cotangent cohomology, this really puts a restriction on the negative parts of the weights that you need to consider. In particular, there's only finitely many different B that you have to consider when you're formulating your weight. Okay, so this is giving us important information about the negative part of the weights that we need to think about. What about the positive parts? So for I equals 1 or 2, we can look at TIC of X. And in fact, I can completely do away with the positive part after replacing X by a different simplicial complex. So this is isomorphic to TI. Now I just have the negative part, so TI minus B. And the complex that I need to take is I need to take the link in X of the support of A. Okay, so what's the support of A? This is just the set of those coordinates of A where the entry of A is non-zero. So here, the support of A is those coordinates with AJ non-zero. Okay, so this is going to be a subset of the set 1 up to n. And so I just take the link of that subset in X. So this will be a subcomplex of X. And I take the cotangent cohomology there, now just with the negative part of the weight. Okay, so this tells us a lot of interesting things. First of all, this cotangent cohomology will be 0 if the positive part is not a face of the complex, because in that case, you'd get an empty link, and cotangent cohomology of that would be 0. Secondly, the cotangent cohomology here doesn't actually depend on A. It only depends on the support of A. And then finally, the really useful thing here is that this allows you to just reduce to the case where you only consider weights whose entries are all non-positive. Okay, so this was statement number 2. And so now somehow we know what kind of non-positive weights we need to consider. It's just entries 0 and 1. And we know that we can reduce to the case of a weight that is only non-positive. What can we say then? And so this is statement 3. So there exists topological spaces U tilde of B, which is contained in U of B, which is contained in the cone over X. Right, so I start with my simplicial complex X. Think about this as a topological space and take the cone over this. So this is a space of 1 dimension higher, such that what is true? So if I'm interested in Ti minus B of X, this is isomorphic to the reduced I minus first relative cohomology of UB tilde in UB with coefficients in K. Okay, so this gives a topological interpretation for this cotangent cohomology. The space that I'm looking at depends on what my weight vector B was. But the spaces that I'm thinking about are all subspaces of some common topological space here. And these spaces are quite explicit as well. And so when it comes time to actual computations, this proves to be a useful computational tool. Okay. So these are the results when I is equal to 1 or 2. And the goal in the rest of the talk is going to be to try to generalize these to higher cotangent cohomology modules, so Ti when I is larger than or equal to 3. Before I start talking about that, let me maybe just help illustrate the utility of this result, mention some prior work of mine. So this is due to Jan Christophersen and myself, and then in a generalized form, it's due to myself, Alfredo Nahira Chavez, and Hippolito Treffinger. And it says the following: let X be a cluster complex of type A, D, or E, then T2 of X is equal to 0. So first of all, I'm not going to say precisely what a cluster complex is, beyond saying that for any root system of type A, D, or E, there's a natural simplicial complex that one can associate. This is connected to the theory of cluster algebras. It's also connected to the theory of representations of finite dimensional algebras, and also to the theory of generalized associahedra. In any case, these are very interesting simplicial complexes. And we show that the second cotangent cohomology module for the Stanley-Reisner ring of these things is equal to 0. And the way we do it is really by using this topological interpretation of cotangent cohomology coming from Altmann and Christophersen. I should say The type A case is the case that was due to Christophersen and myself. And then with Nahera, Chavez, and Treffinger, we give sort of a unified proof that works in all simply laced cases. Okay, so that's the contents of this theorem is a completely different talk. I just wanted to mention it to show that these results of Altmann and Christophersen can be used to obtain some interesting consequences. Okay, so this brings me to part 3, where I want to talk about higher cotangent cohomology. Okay, and so the dream would be to just generalize statements 1, 2, and 3. And so let me start with some bad news. Okay, so the first point of bad news is that statement 1 above fails. So what was statement 1? Going back up, this said that the cotangent cohomology was 0 unless the negative part of the weight vector had entries just in 0 and 1. And so using the tools that I'm going to discuss in a couple minutes, Andrea and Francesco and I are able to compute cotangent cohomology for many simplicial complexes, at least in cohomological degrees 3 and 4. And in particular, if you take the following example, so I take just the simplicial complex consisting of these 3 vertices with no edges and no higher dimensional simplices. This is my x. You can show that T4 of x in degree minus, I didn't leave myself enough room here. So in degree minus 2, 1, 1, this is isomorphic to a copy of your field K. In particular, it's non-zero. And you'll notice here that I have a 2 that's appearing in the negative part of the weight. And so statement 1 simply is not true. Okay, so that was the first bit of bad news. And the second bit of bad news is that 3 also cannot be true. And so let me tell you why. So if 3 were true, let's look at it for a second. Okay, so depending on my weight vector, what my weight vector is, I have sort of these different topological spaces where I'm taking this relative cohomology. But these topological spaces are always living in this fixed space, which is the cone of x. And so that means that if I look at really high cohomological indices, this thing, so for a fixed simplicial complex, x, these relative cohomology groups would have to vanish. And so if 3 were true, this would imply that Ti of x is equal to 0 for I sufficiently large. And this is simply not true. So this is very much connected to this result I mentioned earlier of Ramov, that you always have to add generators in arbitrarily high degree unless you have a complete intersection. And so there are certainly examples of Stanley-Reisner rings where you have cotangent cohomology in arbitrarily high degree. And so this prevents any statement from 3 like having a chance of being true. Okay, so that was the bad news. So let's talk about some good news instead. And so the first piece of good news is that statement 2 is actually true. So theorem, this is myself, Francesco Meazzini, and Andrea Petracci. That says, so let x be a simplicial complex. And we take C to be equal to B minus A. This is our weight vector, and Z to the N. Then for all I larger than or equal to 1, TIC of x is equal to ti minus b. And here I take the link of the support of A in X. Okay, so this is what we call the localization formula. Okay, and so this is a really powerful tool. It allows you to reduce to the case of weights that are non-positive, which is a very useful thing. And when you're doing this reduction, by moving to these links, you're always moving to subcomplexes of your original complex. In particular, the dimension is going down, and this turns out to be very useful when you're trying to prove things like vanishing of cotangent cohomology using some induction or something like this.
Sorry, Nathan, I have a small question. Is B minus A or A minus B? Did you switch?
Oh, yeah, sorry, thank you. That's still A minus B. Yes.
Yeah.
Just checking if people are paying attention. Okay, so that was the first bit of good news. And so now going back to the results of Altmann and Christophersen, we want to see what we can do to salvage 1 and 3. So having this localization formula, this allows us essentially to get rid of the positive part. Now we can focus on things where we only have a weight that has a negative part. What negative parts do we have to consider? And once we figured that out, do we have some kind of description of the cotangent cohomology for them? Okay, and so to state results here, I wanted to introduce a little bit more notation again. So the first thing that I want is to know what a flag complex is. So definition, a complex X is flag if all minimal non-faces are edges. In other words, this Stanley-Reisner ideal IX is generated by quadrics. Okay, so this is certainly a restriction. An arbitrary simplicial complex is not going to be flag, but many interesting simplicial complexes are flag complexes, including these cluster complexes that I was talking about very briefly earlier on in the talk. Okay, so this is a special subclass of simplicial complexes where we're going to have some stronger results. Okay, so this is what it means for a complex to be flag. If I have some weight vector b in Zn greater than or equal to 0, we say that b is of type I1, I2, up to ik, if the non-zero entries of b are exactly this I1, I2, etc., up to ik in descending order. Okay, so for example, if I look at 0, 3, 0, 7, this has type 7, 3. Okay, so armed with these two things, I can now tell you what kind of restrictions we can put on the negative part of the weight to guarantee that cotangent cohomology is vanishing. Okay, so here's our second result. So this is again due to myself, Meazzini, and Petracci. And it says the following. So let X be a simplicial complex. And C equals A minus B, be one of our weight vectors. So first of all, TIC of x is equal to 0. Yeah, here I guess we're going to take I just to be anything larger than or equal to 1. TIC of x is equal to 0 unless... sorry, no, I didn't want to do that yet. So here in this statement, I think I want to take I to be at least 2. There we go. So TIC of x is equal to 0 unless unless B belongs to, so before we had that B had to have entries in 0 and 1, and it turns out that the straightforward generalization of that is that when I'm looking at TI, B needs to have entries in 0, 1, up to I minus 1. All right, so if we think back to the previous result, that was for I equals 1 and 2. When I take I to be equal to 2, this is telling me exactly that B has to have entries in 0 and 1. Okay, and so this is sort of the first way to generalize statement 1 from Altmann and Christophersen, but we can actually do better than that. So if I is larger than or equal to 3 and x is flag, then TIC of x is equal to 0 unless B belongs to 0 all the way up to I minus 2. So we can do even one better. So in particular, if we're looking at T3 and x is flag, we still only need to consider weight vectors B whose entries are 0 and 1. Okay, so it turns out that, as I had said before, sort of having a nice topological description using subspaces of a fixed topological space for arbitrarily high cotangent cohomology is going to be impossible. And so it makes sense to actually focus in on the next interesting cases, which will be for T3 and T4. And so let me summarize what weights we need to consider in these cases. So assume that x is flag for I equals 1, 2, 3, and 4. TIC of x is 0 unless B has one of the following types. Okay, so it could have type 1. So this can happen when I is equal to 1, 2, 3, or 4. It could have type 1, 1. This is when I is equal to 2, 3, or 4. It could have type 1, 1, 1. This is when I is equal to 3 or 4. Or it could have type 1, 1, 1, 1, or 2, 1, 1. This is when I is equal to 4. So if we're interested in describing cotangent cohomology in cohomological degree 3 or 4 for flag complexes, these are the only types of negative parts of the degrees that we have to consider. Okay, so this is what we can do to sort of generalize 1 and really obtain perhaps some stronger results in the special case of flag complexes. Okay, and so now what I'd like to do is I'd like to try to generalize point 3 up above. Let me scroll up to this again. All right, so 3 is giving this interpretation of cotangent cohomology in some non-positive degree in terms of some relative cohomology here of topological spaces that are related to the complex that we started with. And so that's what we'd like to do for T3 and T4, at least in the flag setting. And so in order to do this, I need to introduce a simplicial complex that's related to our original complex X. So here, let's say that X is, as usual, a simplicial complex. Okay, and so now let's take some subset W of my set from 1 up to n. And what can I do? So by X sub W, this is going to be a subcomplex of my complex X. This will consist of all those faces F in X, such that F intersect W is the empty set. And also, I want F to be disjoint from something else as well, namely, so let's look at all vertices V that belong to the set W and take the intersection of the links of these vertices in X. Okay, I want F to be disjoint from this as well. Okay, so this is a lot to process. Let's look at an example. So here we'll return to our hexagon example. Okay, and so let maybe take W to be the subset that consists of these two vertices. Okay, so now if I look at the link of each of these vertices, so the link of the vertex on the left is going to be these two green vertices that I circled. The link of the red vertex on the right is going to be these two pink vertices that I circled. And so the intersection of these two links is the one that's both green and pink. So I need to be disjoint from that. I also need to be disjoint from the two red vertices. And so what I end up with is the blue subcomplex that looks like this. So that here is my XW. Okay, so this is something that you can always form. And this turns out to be very important for considering T3 and T4 of flat complexes. Okay, so here's our next result. So again, this is myself, Francesco Meazzini, and Andrea Petracci. That says the following. So let's say X be a simplicial complex. Whoops. 1 second. Sorry, just let me share my screen again. Okay, sorry about that. Okay, so we have a simplicial complex X. And so first statement, if I is larger than or equal to 1 and B has type, oh yeah, sorry, B of course is in Z greater than or equal to 0 to the n. If B has type 1, so in other words, it has a single non-zero entry that's equal to 1, then Ti minus B of X is equal to H twiddle I minus 1 of this complex X W with coefficients in K. And here W is just the support of B. Okay, so this is for things of type 1. Now, if I is larger than or equal to 2, and B has type 1, 1, and X is a flag complex, then Ti minus B of X is equal to H twiddle I minus 2, again, of XW. Okay, so this lets us deal with things of type 1 and type 1, 1. Let's maybe look at an example of this. And so we'll take our standard hexagon example. And let me take B to have support given by these two red vertices here. Okay, so this is of type 1, 1. So I need to think again, what is this complex XW? Well, in this case, the intersection of the two links is empty. And so the complex that I get is just this blue complex that looks like this. Okay, so it's just consisting of sort of two contractible segments. And so if I look at reduced H naught of this, this will be one-dimensional. So T2 in degree minus B of X is isomorphic to K. And if I look at T3 in this degree, well, this blue complex, it doesn't have any H1. And so this is just equal to 0. Okay. All right, so let's go ahead and look back at this result here, which was telling us which degrees we need to consider when we're thinking about T3 and T4. So we've dealt here with degree 1, or type 1. We've dealt here with type 1, 1. And so there's just these three other cases that we need to deal with. The results here are a little bit more complicated. For 2, 1, 1, there's another complex that I'm not going to describe, where to get T4, you just need to, again, consider the reduced zeroth cohomology. For type 1, 1, 1 and 1, 1, 1, 1, it's slightly more complicated. But again, there are some very nice topological results. And so let me just give an example where we think about this degree 1, 1, 1, which sort of gives a hint as to the kind of complex that we need to consider there. So theorem, again, with Francesco and Andrea. So let X be a flag complex, B in Z greater than or equal to 0 to the n of type 1, 1, 1. Then for I equals 3 or 4, Ti minus B of X is isomorphic to Hi minus 2. Yeah, so again here, W is going to be the support of B. So I'd like to just put here XW, okay, but this is not true. So instead I need to put a hat there. That means there's a slightly different complex. And so I'm not going to tell you precisely what that complex is, but I'm going to tell you what it is in an example to give you an idea of what it's like. Yeah, in any case, there's still a nice topological interpretation in this case. So here, this XW hat is a complex whose vertices are those of XW. And I have to throw in 3 extra vertices. So I'll call it 1 prime, 2 prime, and 3 prime. And so let me tell you what this actually looks like in our example. and then I will be done. Okay, so in the example, again, let's go to our hexagon. Okay, 1, 2, 3, 4, 5, 6. Let me choose my B is going to be 2, 4, and 6. That's my B. Okay, what's my XW? Again, if I look at the intersection of all the links of these things, this is empty, so I just have to avoid the red vertices, which means that I have these 3 disjoint blue vertices. Uh-oh, my tablet is giving me problems again. Sorry. Okay. Okay, and so now I'm going to draw this complex and then we'll be done. So here's my vertex 1. Here's my vertex 3. I also had this vertex 5. I also had these other vertices, my 1 prime, my 2 prime, and my 3 prime. Okay, and so now the complex that I need is I'm going to take edges between all the vertices of XW and all of my new vertices. So these edges, but also these edges. And I also take edges among my new vertices, 1 prime, 2 prime, and 3 prime. So I have all these edges here. It turns out I also have to add in some 2 simplices. So I'll shade them in here. These 2 red 2 simplices, these 2 green 2 simplices, and these 2 dark green 2 simplices. Okay, and so this actually is in this example of my simplicial complex XW hat. It's not difficult to see this deformation retracts just down onto this triangle that I have here. And so this tells me that T3 in this degree. All right, so T3 is going to be H1 of this. And so that's isomorphic to K. And T4 is going to be H2 of this, which is 0 in that degree. Okay, and I'm 1 minute over. I apologize. I will stop now. Thank you for your attention.
Thank you very much, Ilten. That was very, very interesting. Do you have any questions from the audience?
I have a question. So some time ago, Mariano Suarez-Alvarez and I computed, or tried to compute, the quotient cohomology of some Stanley-Reisner rings and their some non-commutative versions, and also Hilbert rings, which also arise from deforming algebra to the straightening law. And we didn't get too far, but we did find some numerical phenomena, such as this, especially for the Hilbert rings. For the Stanley-Reisner rings, it was farther, but we did manage to put some results like this for quotient homology of even case. So I was wondering if you have some results on Hilbert rings also.
No, so we've only thought about Stanley-Reisner rings. I unfortunately didn't get to tell you at all about how we do any of this. And so in 2 sentences, underlying all of our results is that in this situation, we have a very explicit Koszul-Tate resolution that is somehow coming from the Taylor resolution of a monomial ideal. And so I wouldn't know how to do that in the setting of a Hebbe ring. There may be something that you can do there as well, But I'd also be very interested in having a reference to your work on Hochschild cohomology for Hebbe rings, because this would be interesting to look at. So maybe
communication, it was never published or finished or whatever. But
okay.
I'd love to reactivate that and see something, because what we did was we did something very similar to what you just described, except that for Hebbe rings you can use the Koszul resolution of the polynomial ring to get a decent resolution to compute Hochschild cohomology for the quotient. But except that the resolution comes from a completely different place, there's a very explicit resolution, and you can just, very explicit differentials, everything somehow became. We split things in terms of just the C weights, and we had some periodicity results that were saying this is not just going to beat downwards, but also upwards in the so downwards in the weight, but also upwards in the homological index. So eventually the cohomology becomes periodic. And all of this had a very similar flavor, which is why I thought of that.
Okay, that sounds super interesting. So if you'd like to talk about that more, please get in touch.
Maybe I can find some old notes. But also I guess my general question is, you said that this cotangent cohomology things are direct summands of Hochschild cohomology.
Yes.
So can you really identify them inside? So if I compute Hochschild cohomology, can you tell me what the summands are inside? Or if I have a complex that computes Hochschild cohomology, can you find a subcomplex in there that computes the cotangent?
I believe the answer is yes, but I'm slightly out of my depth when it comes to Hochschild cohomology, actually. So I believe the answer is yes, but I'm not absolutely certain.
Okay, because then maybe it's interesting to look at what we did to get those Hochschild complexes. Identify what the tangent sum.
Yeah.
Okay, thanks.
Yeah, thank you.
Do you have any more questions?
Yeah, I have another question. Thanks, Nathan, for this. I mean, it's very enlightening. I mean, the natural question is, can you say something about the associahedron or, let's say, cluster complexes for all types, right?
Yes.
You're saying something for C2 here.
Yes. So in fact, if I had planned so much more, and the next thing in my notes is to say, in type A, T3 is equal to 0 for the type A associahedron. And I imagine that it could be true in type D and E as well.
Okay.
I don't know, because that requires like some annoying, at least type E requires like some annoying sort of cluster theoretic proof like we did that I don't really fully understand.
Okay.
But like for type A, like the combinatorial proof works quite straightforward. Interestingly, so you might expect, oh, okay, so T2 is 0, T3 is 0. Maybe it like keeps on vanishing. It does not. So for T4, if you take the pentagon, that has T4 equals 0. But if you go up to the two-dimensional complex, that no longer has T4 equals 0.
All right. Oh, okay. That's very interesting. And what about type B and C? I mean, you here have in a way type B2, right? And you're showing that B3 is K.
Yeah.
There...
Go ahead.
No. I mean, if you think that we can also say something about other types, like setting these thoughts.
Yeah, I mean, so right. So here we have the hexagon, which is type B and type C. And so we already know that type T2 is non-zero.
Yeah.
We see here that T3 is non-zero. T4 is also non-zero. And
Okay.
I mean, this is not any kind of theorem, but sort of the, first of all, it's like, it's really special when any cotangent cohomology vanishes.
Right.
And but like frequently there are some kind of like geometric, or like maybe there's some reasons from algebraic geometry, coming from algebraic geometry, for why this is true. And typically this will maybe tell you that you get like T2 is 0 and T3 is 0, and like there's some range where you have cotangent cohomology vanishing, and then after that it stops. So I would be very surprised to say, like, for the hexagon, to suddenly have that, yeah, like T2, T3, and T4 are all non-zero, and then to have some higher cotangent cohomology that suddenly is 0 again. I'm not saying that it doesn't happen, but that would be even more unexpected.
Okay. 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 Thank you.
Yeah.
Do you have a question? Oh, you do that here, so it's saying that again.
Thank you, everyone.
Thanks. Yeah.
So